Thing we need to talk about is logarithmic differentiation. So the rules of logarithms will really help us take the derivative of some functions that tend to be a little more complicated. Let's look at a couple of examples. Let's start with 75. We have y equals x square root x squared plus 1. There is a domain restriction here, so we're not going to worry about that. That domain restriction will follow us through the problem. And you'll see why that domain restriction is there in just a little bit. So to do this. Now, if we were to take the derivative normally, we see we have a product rule. To take the derivative of the second piece here, we would have a power rule and a chain rule. Logarithms are going to make this a little bit easier to deal with. So let's look at that example. This is number 75. We have y equals x square root x squared plus 1. So to apply logarithmic differentiation, the first thing you want to do is take the logarithm of both sides. And the reason we want to do that is that logarithms have some very nice properties. And one of the properties is if you take the logarithm of a product, then you can split that up into two pieces. That would be the logarithm of x plus the logarithm of the square root of x squared plus 1. And then we could rewrite this. That square root is the same thing as a 1/2 power. So let's just pull that 1/2 power to the front of that piece. So now this is going to be easy to take the derivative of. The derivative of the ln of y, that's implicit differentiation. That's just going to be y prime over y. The derivative of the ln of y, the derivative of ln of x is 1 over x. And then when we take the derivative of the ln of x squared plus 1, remember it's du over u. So the derivative of our u is 2x. And then our u was x squared plus 1. So I'm going to clean this guy up just a little bit. I see that the 2's are going to cancel in that second term, the 2 here and here. So that's going to leave us with x over x squared plus 1. And then I would like to get a common denominator between these. So we need to multiply that first function by x squared plus 1 over x squared plus 1. And then we need to multiply the second one by x over x. So we have x squared plus 1 over x times x squared plus 1 plus x squared times x over x squared plus 1. So then if we put this together, that common denominator, we have it, so we can add the numerators. So we're going to have a 2x squared plus 1 over x times x squared plus 1. Now keep in mind, that's equal to y prime over y. So to solve this for y prime, we need to multiply both sides by y. And when we do that, we have 2x squared plus 1 over x times x squared plus 1. And that's multiplied by y. Okay, but remember we have a substitution for y. We said in the beginning that y was equal to x square root x squared plus 1. So let's make that substitution. And then now we see that these are going to cancel. So we can cancel the x's. And then this square root of x squared plus 1 and this guy will reduce. So we're going to have 2x squared plus 1 over x squared plus 1 to the 1/2. So there's our derivative. Just for fun, let's do another one. Let's look at number 80. So before we move to 80, I kind of want to talk about that domain restriction again, because you're probably wondering where that came from. That came from taking the logarithm here. So going back, they gave that to us. That's not going to affect how we take the derivative or anything like that, but just to show kind of where that's coming from. When we take the logarithm of both sides, it does change the domain. So because now we've imposed a restriction that this guy has to be greater than 0. But as soon as we rewrite that log, then now we're looking at this guy has to be greater than 0, and this piece has to be greater than 0. So you can see why if we take the logarithm of x has to be greater than 0. You see why they put that in there to begin with. It helps us set up what's going to happen when we take that derivative. Every step that we do, we have to think about domain restrictions. So let's look at another example of logarithmic differentiation. Let's say we want to take the derivative of this guy. So if we took the derivative as is, we would have a quotient rule, and then when we take the derivative of the top, we would have a product rule, and the derivative of the bottom would be a product rule. But logarithmic differentiation is going to make this really just a lot easier for us. So let's look at how we can go about doing that. Our first step is always to take the logarithm of both sides. So we have the ln of y is equal to the ln of all of that. So we're going to expand this before we ever take a derivative. You want to use those logarithmic properties to your advantage. So the first thing we notice is that quotient. We can rewrite this as the difference of two logs. And then we can rewrite that product as the sum of two logs. Same thing with this piece. And then we can distribute that negative to both of these pieces. So all this is equal to the ln of y. So now let's take a derivative. The derivative of ln of y is y prime over y. The derivative for each one of these pieces will be a chain rule. So it's going to be du over u. Our derivative here is going to be 1. Our u is x plus 1. Same thing here. The derivative of our u is 1. Our u is x minus 2. Derivative of u here is also 1. And the derivative of u here is 1. Now I'm going to reorder these. So now we want to simplify. And I'm grouping those difference of squares together because we want to find common denominators. And I'm going to do this step by step. So if we look at the common denominator here, it would be x plus 1 times x minus 1. So we would multiply this first fraction by x minus 1. And then we would multiply this one by x plus 1. So then our common denominator would be over x plus 1, x minus 1. I'm going to work with just this piece, and then I'll come back and catch the other two. So we have x minus 1 minus x minus 1 over that common denominator. I'm going to write it as x squared minus 1. So we're going to have a negative 2 over x squared minus 1. Now let's go back and work with these two. So if we multiply this fraction by x plus 2, we're going to have 1 times x plus 2 on the top. And then when we multiply this one by x minus 2, we're going to have minus 1 times x minus 2 over x minus 2 times x plus 2. So if we were to distribute x plus 2 minus x plus 2 over that common denominator, which is x squared minus 4, we're going to have 4 on the top over x squared minus 4 on the bottom. Okay, so now we need to put these two together. So this guy needs the x squared minus 4. And the second fraction needs the x squared minus 1 over x squared minus 1, x squared minus 4. I'm not going to multiply those together. So we have minus 2x squared plus 8 plus 4x squared minus 4 over that denominator. So we have 2x squared plus 4 in the top over x squared minus 1, x squared minus 4. Now, keep in mind what that's equal to. It's equal to y prime over y. So I didn't copy that down over here, but you can see it's the same thing. This is equal to y prime over y. I did not do anything to the left. I just worked with the right. Now, goal is to solve this guy for y prime. Let's multiply both sides by y. And when we do, we end up with this. Okay, but remember, we have a substitution for y. We said in the beginning that y was equal to x plus 1 times x minus 2 over x minus 1 times x plus 2. So let's make that substitution. I'll call this SUB for the substitution step. So we have 2x squared plus 4 over those difference of squares. Now I'm going to factor those guys back out in hopes that something's going to cancel. And then we're going to multiply all that by y, which was x plus 1 times x minus 2 over x minus 1 times x plus 2. So you can see that this x minus 2 will cancel with this x minus 2, and this x plus 1 cancels with this x plus 1. So then we are left with 2x squared plus 4 on the top. Check out what's in the bottom. We have x minus 1 times x minus 1, which is x minus 1 squared. And then we have x plus 2 times x plus 2, which is x plus 2 squared. So there is our derivative. Sometimes taking the derivative can be easier, especially if we have a lot of things that are multiplied together or things that are divided. just because we can use those properties of logarithms if we take the log of both sides, it'd make life just a little bit easier.